Let's talk about Sidekick protocols, in-network assistance for secure end-to-end transfer protocols. So imagine you're on your laptop using the Wi-Fi on a moving train. Your laptop is connected to a router or an access point on the train over a lossy wireless link, and this router in turn connects you to the rest of the internet, such as an end host on a cloud server. As one might imagine on a moving train, the Wi-Fi seems really bad. Your WebRTC audio call with a friend is suffering from lots of drops and delays, while your file upload using the QUIC transfer protocol is taking a really long time. Surprisingly, though, your TCP upload is actually very fast. And the reason this is surprising is because TCP is a dinosaur that was invented with the internet, versus QUIC was invented at Google in 2012. It's constantly evolving and developing, and your laptop is actually using the newest and greatest version of it. But as the loss on the wireless link increases, the performance of QUIC actually dramatically gets worse. TCP, on the other hand, is able to use almost all of the network capacity and only starts to slowly deteriorate as the loss percentage gets even higher. So what's the difference between these two? QUIC is what we call a secure transfer protocol. All the data is completely encrypted on the wire. TCP, on the other hand, while its payload can be encrypted, information in its header, like the sequence number and acknowledgement number, are always visible to middleboxes on the path. For secure transfer protocols, all transport decisions are made end-to-end. And they're blissfully unaware of the details of the network path. But if we take a closer look at the network path, the router actually divides it into two very distinct segments. The first is a lossy wireless link, and the second is a more reliable but higher latency cellular path. Now, with TCP, middleboxes can not only see the information in the transport headers, they can actively manipulate them. In this example, TCP intercepts the initialization packets of the TCP connection, and instead of allowing the end-to-end connection to form, it forms two separate split TCP connections with itself and each of the end hosts. These two split connections allow the middlebox to customize the performance characteristics of the connection based on the particulars of each path. And this is the basis of what we call a split connection TCP PEP, or a performance enhancing proxy. And actually, these kinds of PEPs are very common today. You can find them on 20 to 40% of internet paths and almost all cellular paths. So if TCP and PEPs is so great, why does QUIC exist at all? And that's because there's a dark side to performance enhancing proxies. So middleboxes have come to expect a certain wire format from our transfer protocols like TCP, and this has made it very difficult to change and upgrade transfer protocols like TCP over time. And this is a graveyard of all the ideas that a lot of the ideas that have been hindered because of how PEPs exist today. And the closest we've really come to solving this problem are some research proposals. And they propose co-designing PEPs and transfer protocols so that they can explicitly allow help or explicitly credential the PEP to access certain fields. But this kind of ossifies the protocol before they can even be deployed. And so the status of what we have today and what we've already seen is that a lot of modern transfer protocols today will totally encrypt the transport layer, avoiding the problem of protocol ossification. But as a result, they give up on PEPs and all the performance benefits that go along with it. So this leads us to our question. Can there be a universal PEP for arbitrary transfer protocols? Is there a PEP that can be deployed for all existing transfer protocols and a PEP that leaves these transfer protocols free to evolve over time? Our proposal is a new architecture for this type of in-network assistance. Instead of manipulating the data on the wire, the middlebox instead just sends information about the underlying connection back to the end host. And it sends this information on an adjacent connection. This really decouples middlebox functionality from the underlying transfer protocol. And it empowers transport decisions to be made at the host. Now, what kind of useful information can a middlebox send on the Sidekick protocol? This kind of question is easy to answer for TCP, which has some clear text sequence numbers. You can just say which packets the middlebox has received, and you can do that using a range over these clear text sequence numbers. But when the packets look random, this problem is a little harder. We can map these random payloads to 32-bit identifiers of the packet, but even then, since they're no longer sequential, we can't say that we've seen a range of packets, and we can't even say if a packet is missing in the connection. Our solution to this problem is a way to actually acknowledge these sets of effectively random packets. And we have a way that provides several non-trivial properties, such as being concise and efficient, that make it practical to use. And we call this a QUAC. Now, once a sender receives a QUAC, what should it do with this information to obtain a performance benefit that's similar to these Peps today? So QUACs describe which packets have been received and where, and thus it implies which packets have been lost. And with this information, we can enable a whole set of new kind of path-aware sender behavior, including new retransmission policies, flow control policies, or congestion control algorithms, informed by this new signal from the network. So in the rest of this talk, I'll talk about our two technical ideas that really make Sidekick, this architecture of Sidekick protocols, possible. One is how to efficiently acknowledge a set of random packets called a QUAC. And another is we'll focus on a new type of congestion control algorithm that incorporates idea of where loss is occurring. And then I'll also talk a little bit about our implementation. All right, so what do we want from a QUAC? The first is that QUAC needs to be concise. It needs to add a little additional overhead onto the link. It also needs to be efficient. The middle box needs to be able to quickly process packets, and the sender needs to be able to quickly decode the information in the QUAC. And formally, we want to decode the set of received packets at the middle box, given the set of sent packets at the data sender, given the QUAC and this list of sent packets. And then finally, we want the QUAC to be resilient to loss if we were to lose the QUAC on the Sidekick protocol. And we can achieve this by having it be a cumulative representation of all the packets the middle box has received. How might one construct a QUAC? Well, the first idea we might think of is to echo every single packet that we've seen at the middle box. But this uses a lot of this uses a lot of space on the Sidekick protocol. And it's also not resilient to loss, because if we lose one of these QUACs, then there might be a spurious loss. Now, a second idea might be for the middle box to send a hash of every single packet that it's ever received. And then the sender, in order to decode this hash, it takes every subset of packets of the same size, hashes all of those until it finds the same hash. And hopefully you can kind of see that this takes a really long time and gets even slower as the number of packets and missing packets increases. And so that's also impractical. And so our solution, the QUAC, is based on it's inspired by some related algebraic work solving the problems of straggler identification or maybe set reconciliation. And the idea behind it is to represent the missing packets in a connection, those that are in the set S but not in the set R, as a system of power sum polynomial equations. And our QUAC is able to achieve these four properties that we've expressed. And so I'll go over some of the details here and end with some intuition. But the most important state that is maintained at each of the middle box and the sender is what we call a threshold number of power sums of either the received packets or the sent packets. A power sum is just mathematically defined as this. And this threshold is an upper bound on the number of missing packets that we can allow. And this can be estimated based on the network configuration and also updated without any side effects. The middle box and the sender each maintain some additional state. And all of this state on the left side of the middle box is what we call a QUAC. The middle box repeatedly sends these QUACs to the sender. And then the sender needs to decode the information in the QUAC. And the high-level idea from this algebra, which you can find more in the paper, is that we get a set of m equations in m variables, where m represents the number of missing packets. And we can exactly solve this equation to find these missing packets. OK, so now we have a way to acknowledge a set of random packets. Next, I'll talk about a path-aware congestion control algorithm. So just some background on congestion control, or how I view it, is congestion control really wants to balance two conflicting goals. One is to use as much network capacity as possible, and the other is really to share the network fairly with competing flows and to avoid congestion collapse. QUIC, as many of you probably know, is one of the most popular congestion control algorithms out there. The idea behind the QUIC algorithm, which is implemented at a sender, is that it modulates something called a congestion window, which represents the number of outstanding bytes in the network. And it decides whether to increase it or decrease it based on ACKs. And the reason it increases or decreases it is it interprets loss from these end-to-end ACKs and then uses loss as a signal of congestion. Now, recall from before that QUIC is a lot slower than TCP in this scenario on the train. And if we think about what they're doing, both QUIC and TCP are using QUBIC as congestion control. QUIC has one end-to-end connection, and therefore it has one qubit congestion window. And what TCP is doing with these split connections is actually a little weird. Since there's two TCP connections, there's actually two congestion windows. And so what we call, so the congestion response that's actually happening in this connection is something we call split QUBIC. And you'll notice that if you remove the TCP PEP from the TCP scenario, TCP will perform similarly to QUIC when they are both end-to-end, because they're both running QUBIC. Now, we want to obtain a performance benefit for our connection for QUIC. And now we have some information from quacks. So what can we do? So one thing we can do is to, well, retransmit the packets that we've observed lost from quacks, but do the same congestion response before. Treat the loss as if it came from an end-to-end ACK. But this doesn't get us anywhere because the performance is the same. The other option is to ignore the fact that a loss occurred. We can retransmit the packet, but we can just not update anything about the congestion. And so the end-to-end ACKs also won't tell us that a packet is lost. And so this gives us great performance. We're always utilizing the full link. Except this isn't fair, and it'll actually cause congestion collapse if we just repeatedly retransmit packets without any congestion response. So this kind of motivates our need for what we call a path-aware congestion control algorithm. And the idea behind this path-aware QUBIC is that we want to be as fast as we can while not exceeding the fairness or aggressiveness of TCP with a PEP. And so we want to emulate the behavior of what's going on in this split TCP QUBIC connection while being quick and having one single end-to-end connection. And so QUIC with the Sidekick still only has one congestion window, but we want to emulate the behavior as if we had two congestion control windows. And yeah, so the intuition behind that is what can we do to the QUIC QUBIC algorithm so that when we're modifying the congestion window, now knowing whether loss occurs on a path segment that's close to you or far to you, how to emulate the behavior of a split TCP PEP. But even if all this is a bit confusing, really the high-level idea we want is that now we have a new signal about loss in the network. We know where loss is occurring, and we can use that to improve our congestion control algorithms in a fast and fair way. OK, finally, what do we need for Sidekick protocols to actually be practical? What did we implement? And so our implementation is all open source. We won the community award for it. We implemented a library for using the quack. We implemented a binary for the Sidekick to send quacks. And we had some client integrations, and all our experiments or code are on this website. And if you're interested in the particulars of QUIC, we encourage you to check our code out. Yeah, so our binary at the middle box, it takes about 74 cycles per packet to process a single packet to update the state related to a quack, since it's just a few arithmetic operations. Largest overhead was reading the packet from the NIC, and in our binary, we achieved a throughput of 464,000 packets per second for a single core. Yeah, so the most interesting part about our implementation is our client integrations. So we have two clients. One is a simple media server and client for making audio calls, and our second one is QUIC and HTTP3 client and server. And for our QUIC client, we integrated it with both the libcurl client for HTTP3, and then the Cloudflare implementation of QUIC called Quiche. And so there's two parts to a client integration. First, you need to establish a connection, the Sidekick connection. And the second, you need to implement the stuff that we call the path-aware sender behavior. And so in QUIC, there's sender behavior for retransmission, so retransmitting QUIC packets, QUIC data that has been lost in a new QUIC packet. We have our path-aware congestion control algorithm, and we have some flow control logic. And these types of path-aware sender behaviors can be toggled on and off based on the particular network scenario or application objective. OK, and the overhead at the sender of a QUIC client is about 3%. And these are the additional quacks that the sender has to process, in addition to the ACKs that it already receives. We tested these two clients in 3 different scenarios in emulation. The first scenario is is the WebRTC audio call that we described on the train. You're having an audio call with a friend, and you'd like your packets to be retransmitted more quickly on that wireless link so that your friend can experience better audio quality. And then the second is our second scenario on the train, where we have a quick file upload. And now with information from the QUIC, we can have a more informed congestion response and upload our file much faster. In the real world, we didn't actually ride a moving train, but we did deploy a Sidekick on an access point in our computer science building, and we used our laptops through this access point to access some servers in the cloud. And in this real-world scenario, we're able to achieve similar reduced de-jitter buffer latencies and improved upload throughputs while being more robust to these more variable network conditions. And so, to conclude this talk, Sidekick protocols are a new way for in-network devices to provide assistance to end-to-end protocols, even when they're totally encrypted. And QUICs enable these senders to emulate the behavior of Peps while making all the decisions at the host. And I'd like to thank all my wonderful collaborators from Stanford and the University of Oslo. And I'm happy to take any questions and also give a rubber duck to anyone who wants one.